All right. Okay, so the lecture is AC, DC, and DC AC converter. AC to DC converter is also called rectifier, and DC to AC converter is also called inverter. So in this lecture, I will first introduce some key terms like power factor and measurement. Then I go to rectifiers. And the last, I'm going to show inverters. The first part about some metrics for measuring the performance of your system, meaning to say the power factor and measure of distortion. But first, you need to know some key properties. This one, orthogonality. Orthogonality means, if you say x and y are orthogonal if integral from a to b of x and y is 0. Okay? It means that these two functions are orthogonal over interval a b. For example, if you compute integral 0 to 2 pi of sine m omega t and sine n omega t plus phi, and if m and n are integer number, then these signals are orthogonal. Okay. Another example, if you have sine function and cosine function, even though you have the same frequency, okay, the integral over a period is also 0. Okay. So please notice these important properties or identities. Any trigonometric function that have different frequency and all different but multiple of one is multiple. No, sorry. I mean, the condition is that m and n have to be integer number. Okay. Then the integral over period is 0. So, and then if you have this one function, the same function sine omega t, but you have a phase shift phi, then the integral over a period is not 0. Okay, equal to this. It can be 0 if phi equal to pi over 2. Okay, if phi equal to pi over 2, then this one become cosine like this. Right? Yeah, this is very important property. Yeah, this definition will be useful for calculating power. Example for this one, you have a resistor as a load, and you have resistor at the wire, but this one is usually very small. Just consider in ideal case and assume it to be 0. If you have the input power source AC, alternative current, in like this, sine omega t, then when we find the power, so P, the instantaneous P equal to V of t times I of t, right? And then the average value P, capital P, equal to this. Then we apply average value, which is 1 over period. Okay, 1 over period, integral over the period, right? Average value. And because relationship between I and V is just different by R in the denominator, right? And then we can have the square term of sine omega t. When you have square like this, yeah, like I said earlier, actually, if yeah, like this one, you have sine omega t plus phi. If phi equal to 0, you have the sine square, right? You have sine square, then the integral here would be cosine of 0 would be 1, so you get 1/2. It means sine is not orthogonal to itself, so integral over a period is not 0. Okay. Well, then so you have the final result of this integral to be like this: 1 over r times all of this square, and then we call this integral as root mean square value. When you compute this, means you compute the root mean square of the voltage. Why root mean square is important? Well, when you know that the electricity source from the socket, okay, from the EDC, electricity you say it's 220 volts. In Europe also 220 volts. But how do you know that 220 volts? Because it's sine wave. Okay. Then the terminology to quantify the voltage of that, you need to use this integral to compute it. So when you compute using this way, you will get 220 volts. Okay. And if the current root mean square of current is 10 amps, right, then you get power as 2.2 kilowatt. Yeah. So when you say you want to quantify voltage current for the AC source, you always use the term root mean square. Okay? But you don't know, right, before. Okay. So here it means if you apply 220 volt AC and you choose the load such that the current would be 10 amps, it means you get 2.2 kilowatts from the wire, okay, the wire power from the socket, right? This is a proof to show the orthogonality. Okay, I think it's just simple integral, just simple calculus. I don't need to explain it in detail. And now let me go into detail of root mean square term. From this formulation, okay, the term root mean this one, right? And mean value means you apply the average value using this integral over a period. Okay. Square means you have the function square. So the name is straightforward, right? From the name you can write the formulation. Root mean square. Okay. Example for sine wave, and then apply the root mean square formulation. Finally, you can show that the maximum of the amplitude of the sine wave here equal to square root of 2 times the root mean square value. So it means the voltage from the wall, from the socket, 220 volts. And if you want to look at the sine wave waveform, yeah, you can use the oscilloscope to check, and you can see this amplitude is actually 220 times square root of 2. Okay, this is what it means. We don't say the maximum voltage of that sine wave, right? We say 220 volt actually equal to the maximum divided by square root of 2. Okay. Okay, next let's use AC source with inductor. And so from differential equation we can solve that the current go through inductor to be this. Yeah, actually because we only have one element, because we assume that this to be 0, just consider in the ideal case, then the current can be found using the definition of VL equal to LdI over dt, and VL is just the same as V source here. Okay, then from this you can use the integral, because the source is sine, then I is cosine, you use integral, right? And then if you apply average power, okay, you have formulation of power, and then you find average, you apply average value, okay, then you get 0. So what does this imply? You have AC source and you have inductor. You measure the average power on the inductor, it is 0. What does this mean? It means inductor does not dissipate any energy. Inductor does not produce any extra energy. It can only store and discharge the energy. So the average must be 0. It means it stores X amount, it will release X amount. So in average, it must be 0, right? So that's why be careful when be careful. You need to analyze deeply. Let's say, well, if there's no power and on inductor, and then you assume that there's no current, and then you careless, you may get your device destroyed, or maybe you get electrical shock if you touch it. Okay, so just be careful when you work with the AC voltage source. And yeah, also in this case you may say, oh, there's no power to the inductor, then the fuse must be safe. No, the fuse is going to be destroyed if the current is too large. Okay, so current destroy the fuse, not the power on the inductor. Yeah, okay, this is how we compute root mean square current. So actually, yeah, the root mean square current is 50 amps with this source and this side of inductor, right? So this current destroy the fuse. Yeah.
Once again, what is VS prim?
VS actually not prim, but not yeah, because last time I did not delete this mark from my pen. Okay. No VS prime, but VS only. VS is the amplitude of the sine wave. And okay, so here, when you get the average power on the inductor 0, what can you say about it? The way you use the power, you use your source is not based on utilization. Okay, why this? It means let's say you have inductor and then you have other component that you want the power to transfer to that component. But if inductor is too big, much of the power is stored in the inductor but not used with other component that need the power. You understand the concept? So it means you utilize your source not well, and you calculate the power factor would be small. Yeah, it would be very small. Okay. Yeah. Yeah, it's kind of like if you have arm of an excavator, but the arm is not rigid enough. Let's say if it's flexible, then you cannot work good, right? The excavator cannot excavate the soil because it's flexible, right? It's too soft. Even though the power of the engine is very strong, right? This is not good utilization. Okay. And how to calculate the what is the metric to evaluate the utilization, whether it's good or not? Yeah, the metric is power factor, which is the ratio between average power and apparent power. What is apparent power? Apparent power is the ability that the source can provide. Okay. The power that the source generate, apparent power. And average power is the power that is dissipated by resistor. Okay. So let's say you have a genset, an engine with a generator. The engine can, the generator can generate, let's say 1 kilowatt, but then when you use with the heater, let's say the heater it consume only 500 watts, which is half. So it means the power factor only half. Okay. Let's say the heater is used by your client, your customer. So they're gonna pay according to the 500 watt, right? But your engine can actually generate up to 1 kilowatt. So it means you have 500 watts not useful. So you don't get so much money from your client, right? And then you can imagine to extend it to a larger power source. For example, from electricity decompose. So when they have substation, then each substation need to check the power factor to make sure the power factor is as high as possible. It means good utilization. All right. So actually, we want power factor to be 1. Yeah. You can get power factor to be 1 if your load is purely resistor. Okay? But as long as you have inductor, you have capacitor of the device and component, then power factor is less than 1.
So the real power is the amount of power that we use?
The real power that dissipated at the resistor of the load. And the only power that show on the watt meter. Okay, that average power. Because the power in the inductor it store and then it release back, right? But when it store, it make the consumer consume less. Okay, something that actually in terms of energy you don't lose energy. But in terms of power, let's say if you have 1 kilowatt, actually you can supply to 2 customers. But one customer use it badly, they have inductor, and then you can only use with 1 customer. The other customer cannot use at all. You understand this point? But if they both use only resistor, then you can provide the service to both customers. So in terms of income generation, time is very important, right? Even though the energy from your engine is not consumed when you use 500 watt, but the time passed already. It's like if you can use both customer at the same time with 1 kilowatt, then you can earn more income, right? That's why we use the term best utilization or worst utilization. I mean, not well utilization, for example, if power factor is less than 1.
For the PX equal to 1, is that the ideal assumption? Or
Yeah, it means no inductor, no capacitor at the device. But it's not the case because when we use motor, and then it has a winding, it has an inductor, flux leakage. Use transformer, also there are some flux leakage, so we cannot have the ideal case. So in practice, if you can get a power factor up to 50 or 85%, that's considered good. 85 or above. All right. Consider a rectifier. Yeah, so rectifier means you want to convert from AC, here AC side, here is DC side. Okay. So DC, it doesn't have to be straight like this. As long as you have only one side like this, it's DC. Okay. But anyway, for operating most of the load, resistor load, you want it as straight as possible. Okay. And here rectifier bridge, this is just symbol as a bridge. So in here you have collection of diode that connect in a way that you can convert from AC to DC like this. Okay, so AC is like this. Okay, so the current at the DC side is periodic steady state, yeah, periodic. So we can use Fourier series to interpret it. This is just a way to compute the the distortion. Okay, maybe I should introduce this term first. If you have voltage V like this, oops. You have voltage waveform like this, and you have, from the source, and you have current from the source to be the same form like this. It is good utilization. Okay, this is good because there's no shift, right? This is sine wave, this is also sine wave. And if you have current to be like this, maybe I draw again together here. If you have current to be like this, not so good. And if you have current to be like this, even worse. Why? Because the shape of the blue is too much different from the shape of the voltage. The blue for the current. Okay, so this is called distortion. If you have a pure sine wave, you don't have a distortion, right? Because we refer to the voltage, and the distortion can be interpreted by the higher term of Fourier series. Because the first term is sine wave, right? The first term when n equal to 1, I don't say the zero term, the first term. The first term is pure sine wave, so it means it look like this one. But the second term also sine wave, but different frequency. Okay, even current have higher frequency like this, also bad utilization. So the scale wave of current like this can be interpreted by the sum of this, all of this. It means sine wave, many sine wave, different frequency, and then it can shape the form to be square as long as it's periodic. So only the first term that has pure sine wave look like this one contribute to the power factor. But the other term with the high frequency sine wave does not contribute to the power factor. That's why when we compute power factor, finally we only have I1 appear here, because I1 is times sine omega t unequal to 1. It's pure sine wave like the voltage waveform. Okay? Other does not contribute to power factor. So it means the distortion would be quantified by the second term to higher term, right? The first term already contributed to the power factor, but the higher term do not. Okay, so distortion from all these terms. Yeah, so finally actually power factor is just I1 root mean square over I root mean square. Okay. I1 root mean square, and then this one cosine. Where I got the cosine? Yeah, okay. I think I miss here. I miss this cosine here. Cosine phi 1, right? Okay. I just explained earlier. If I is sine wave like this, it's good. But if it's already sine wave, but it's shift by angle phi, then it is also not good, right? This causes power factor to reduce by a factor of cosine of that angle. If this angle is 0, cosine of 0 is 1. It means power factor is big. Okay, and we can name the power factor of the ratio between I1 root mean square and I root mean square as a distortion factor, and k theta to represent the phase shift. Then we call displacement factor. Okay, see, you see displace from crossing the origin to crossing here. It displaces. Okay, so we call it displacement factor. Yeah, here just to illustrate again, if you have a periodic current and you expand by Taylor series, okay, I of t equal to I0 plus I1, and I1 actually just some I1 amplitude I1 and then time sine omega t, and this, okay, plus dot, and this is this one. Okay, if you have phi 1 like this, then it would be like this. Okay, yeah, or here, illustrate here. Yeah, phi 1 here is to refer to the voltage. Okay, because your current I here already shift by phi 1 like this. That's why the first term you have shift the sine wave by phi. This should be phi 1. Okay, okay, let me show all, not that, this one first. The next terminology is total harmonic distortion. Yeah, like I said before, the only I1, okay, only I1 contribute to the power factor, and the remaining, the higher order term does not contribute to power factor. It means the higher order term refer to distortion. That's why we use the term total harmonic distortion, and equal to actually square root of this sum. You see the sum except 1, except n equal to 1, because n equal to 1 already contribute to the power factor. Okay, and yeah, denominator is the I1 itself. Okay, so we can manipulate this expression. Finally, we can have distortion factor KD is a function of total harmonic distortion. Okay, but many times you need to calculate this, or from here you can also find total distortion in terms of KD, right? Because KD is I1 root mean square over I root mean square. Yeah, you can easily compute this actually. You can easily compute KD, and THD can be computed from this equation. I mean, it's better use this one to find this one in terms of KD. How you get this one? How can you calculate this one? From the Taylor series expansion, you know the amplitude of the first harmonic, right? And this one from the original current I waveform, you can calculate it using the formula of root mean square. Okay, so KD actually can be easily calculated. After that, you can calculate total harmonic distortion, because it's not easy to calculate using this way, because you use all the term of harmonics from the Taylor from the Fourier series. Cannot. This is example. Let's say the voltage source is Vs sine wave and the current is square wave, but this square wave does not have displacement. It starts from 0, just like the sine wave here. Alright, and given the highest amplitude of the higher value of I is IPK. PK mean peak. Peak mean highest. And then the Fourier series, this one is obtained from Fourier series. Okay, I assume that you already learned it from the mathematics class. So you have In as a formulation in terms of n. Then you can also calculate I1, just substitute n by 1, right? I0 is the average is half here. Okay, because the period is 2 pi and half period is pi. Okay. Now you calculate I root mean square using the formulation. Okay, roots, mean, and square inside. Then you have this value. And I1 you got from this formulation, n equal to 1, right? And root mean square is just I1 over this I1 over square root of 2. Then finally KD equal to I1 over I1 here over square root of 2, which is I1 root mean square. Yeah, actually this one is I1 root mean square. This one is I root mean square. Okay, so this ratio is KD. Yeah, this is how you compute KD, and then you can compute total harmonic distortion, okay, in terms of KD. All right. Yeah. So I already explained, but I don't calculate here for you, right? Okay. Okay, now let's look into more detail of power factor for a rectifier, but before that let's review this a little bit. You have a AC voltage source and you use with the resistor. The waveform of voltage and the current is the same. Okay, so this power factor must be 1 base utilization. And now you use converter from AC to DC. For sure that the current, because the current here more or less has similar waveform of this one. I mean similar because we want here as a DC as straight as possible. If you have current straight here, the current here also like straight, but it can be it can both direction. Okay, it can be to this direction or can be to this direction. For this one only one direction. If just one direction, you get straight like this. But this one can be both direction. Then you can have ID or minus ID. Right? ID here, ID. So that's why you get like a rectangular, like square wave. We usually call it square wave. You have ID and then you have negative ID, like this, for the AC side. Okay. So in this case, power factor is less than 1 for sure, because we have distortion of the current waveform. And again, the first harmonic, if you use Fourier series expansion of this, you get first harmonic like this, and this one contribute to power factor. How about this one? You do with inductor. The phase shift from the phase shift of the waveform of current from voltage is pi over 2. So in this case, power factor is 0 volts utilization. How about capacitor? Capacitor also the phase shift is negative pi over 2. Okay, negative pi over 2. So power factor is also 0 because capacitor also store and release energy. Okay. But the good thing is capacitor and inductor work oppositely. One is making the phase shift to the positive. The other one make the phase shift to the negative. So if you use both of them, they may cancel out each other. Okay. It's kind of like if capacitor store energy, you can say energy or power. Inductor discharge the energy or power. So this one work like oppositely. Okay. Then you can use, you can maximize the utilization. You can have power factor close to 1. Okay, so the next part is about passive power factor compensation. Yeah, the idea is just like I said earlier. You use capacitor to compensate the inductor. This is how you construct your circuit. Let me explain this kind of distribution of the power. So you got from the power plant, and then the power plant transform into high voltage in order to use small cable, and then you distribute to long distance using this small cable, but very high voltage. It has to be very high, and then you use transformer to drop it to like medium voltage. You use medium wire, but then you have another substation to drop the voltage to just the range of 240 volts for residential use. Okay, so here at the substation, you want to have good utilization, right? Because residential house may use passive device like inductor or capacitor, but most of the time inductor, because you use big motor in factory, for example. Okay, workshop, machine shop, they use very big motor, and so here the distributor need to compensate. Okay, they use the capacitor in here, and they call capacitor bank to compensate inductor. This inductor. Okay. So look at this terminology. In order to easily analyze passive power and active powers, we can use impedance. Impedance. We analyze in the complex plane. So the average power represented by the real axis. Okay, quantify it on the real axis, and the passive power, okay, or the reactive power, quantify on the imaginary axis. Okay, and the leading and lagging phase, if it is capacitive, it is leading. Leading means the phase is negative like this. If it is inductive, the phase is lagging. It means phi is like this, positive side here, negative side here. Okay, so the source generates the power S, and we call it apparent power. Okay, real power, which is V root mean square I root mean square times the shift of the phase. Okay, the shift of the phase depends on how much you use, how much inductor you use, how much capacitor you use, right? Okay. So power factor is defined of this cosine phi here, because the ratio between real power, real or average, same, real power and apparent power. You can say this, you can say this, you get only this term. Okay, so this is power factor here. And reactive power, apparent power is equal to apparent power times sine of phi, because this is Q. This segment is Q and this segment is P. Okay, we interpret these two in a right triangle, so it is easy to analyze. So here, how do we start to have this complex, plane, in terms of the actual value, especially angle phi, how you get phi. Here phi, here supposed to be phi as well. First, when you started by draw a right triangle and you label the impedance. This edge you label as a resistor. Impedance of resistor is R, and then the imaginary axis or this edge of triangle you label as impedance of inductor, which is L times omega. Okay, impedance, and then you can find this angle easily. This is angle phi. See, and this hypotenuse can be easily calculated by this formulation as well. And then you can draw the same thing for real power and reactive power on this axis, the same angle phi. Okay, and so how you calculate current I? So current equal to voltage divided by impedance. We talk about root mean square value. Okay, when we talk about root mean square value, we say, okay, V root mean square here, and I root mean square, it just equal to V root mean square over the impedance. Z is complex number, but this is the norm of Z, so which is actually root mean square over the square root of R square plus L omega square. Okay, yeah, this is actually Z, norm Z, impedance. I write down here Z equal to R plus J omega L. Okay, yeah, this is the easiest way to calculate power factor. If you use differential equation to solve solution for current, it takes so much time, so many process. Yeah, like I said, the average root mean square is just like this, but the I in function of time actually to be like this, because root mean square. Okay, let me recall root mean square of this one. V root mean square equal to what? Equal to just the maximum divided by square root of 2, right? How about root mean square of I here? Root mean square of I here is just its maximum, which is Vs over square root of omega square L square plus R square divided by square root of 2, right? And this one is just V root mean square, right? This one is just this. Okay, and so apparent power just V root mean square times I root mean square. Phase, yeah, can be easily computed from this, just arctan of this over this. Then power factor, it's just cosine of the arctan. But anyway, cosine you can also look at. Cosine at this angle is actually R divided by the hypotenuse. See, so it's very easy to calculate power factor, right? Two minutes left. Let's say if you have very complicated electrical circuit like this, actually when you use impedance Z as a complex number, you can add all them up, real part with real part, and imaginary part with imaginary part, and finally you just can have equivalent circuit like this. See, so all of this can be simplified to be equivalent circuit like this. Okay, because finally any complex number, finally you will get this form, right? Real part plus J and imaginary part. That's it. And then you consider this one is from this inductor L omega, and this term is just from this R. Okay. This is very similar, I mean almost same thing. Okay, what about for capacitor? Yeah, for capacitor, because for the capacitor you don't have the real part at all, you don't have resistor, right? But you know the phase shift is, because it's purely complex number, it's on here. And then you have the phase is minus 90 degree here. And then you can write down the steady state current I. You can actually find from integration or something, integration or differential equation, but maybe no need the differential equation because you only have one element. You can integrate it directly to get this, and again you can use apparent power V root mean square times I root mean square. You get this. You can compute this, and then reactive power okay, Q prime equal to apparent power times sine of the phase, then you get this, right? And when you assemble the brand of R and R with the capacitor, because you are trying to compensate between capacitor and inductor, right? Yeah, so you assemble them, then the real power obtained from this branch here, and reactive power also from this branch, but from L, effect of L. And for this branch you have another reactive power, so you can add them up, the imaginary with imaginary, then you try to compensate by setting this to 0. So by setting to 0, you can you can finally, maybe I go to the last part, you can finally find C equal to this in terms of R and R. Okay, yeah, same thing, right? So sometimes I like to explain by writing, sometimes I show this immediately. Yeah, this is how you compensate effect of inductor by capacitor bank. And in actual practice, when you see the power factor drop, then you change the capacitor bank to other value. You may manually change the value, but if you can build a sophisticated algorithm that can adapt automatically, so it's online control, okay, it can adapt. And for that, to design a control system, you need to learn control theory in the next semester. Okay, that's all for today. Any question? I can take one or two.